Will time ever stop? It's a question that haunts scientists, philosophers, and poets alike. But before we chase the end of time, we must first ask a more fundamental question. What is time? Because depending on how we define it, time may never stop, or maybe it already has. Let's begin. Chapter 1. What is time? For centuries, time was seen as absolute, steady, dependable, and universal. Absolute, true in mathematical time, of itself, and from its own nature, flows equably without regard to anything external. That was Sir Isaac Newton's view. To him, time ticked on like an invisible clock, flowing forward, untouched by matter or motion. But this view wouldn't last forever. Chapter 2. Einstein changes everything. In the 20th century, Einstein shattered the idea of a universal clock. His theory of relativity told us, time is not separate from space. They're woven together in a four-dimensional fabric, space-time. Time bends, time slows, time stretches depending on gravity and speed. Imagine two twins. One stays on Earth, the other travels near the speed of light. When they reunite, one has aged years, the other, maybe only months. Time, it turns out, is relative. There is no single now across the universe. Chapter 3. Time in quantum mechanics. But the mystery deepens. While relativity made time dynamic and flexible, quantum mechanics treats it like an afterthought. In the quantum world, time doesn't evolve. It just is. It's a background parameter, an external clock. We ask, what is the probability of finding a particle here at time t? But we never ask, what is the probability of time? Because time, in quantum mechanics, isn't an observable quantity. It's classical, fixed, absolute. So, who's right, Einstein or Schrödinger? Chapter 4. The Wheeler-DeWitt equation, where time dies. And then, time disappears entirely. In the Wheeler-DeWitt equation, a candidate for unifying gravity and quantum mechanics, there is no time variable. None. The equation describes a timeless universe, a frozen wave function. Nothing evolves, nothing moves, no ticking clock, no before, no after, just being. Some physicists believe this means time isn't fundamental. It might emerge only when we look at parts of the universe, not the whole. So perhaps, time is an illusion, a trick of perspective. Chapter 5. The photon's perspective. Even now, we must ask, time, for whom? For massless particles like photons, time doesn't pass at all. From our perspective, it takes years. From a photon's frame, zero time, no aging, no moments, just now. So when we ask if time will stop, we must ask, for whom? For us? For particles? For the universe? Chapter 6. Will time ever stop? Possible scenarios. 1. The Big Rip. One theory, the Big Rip. In this scenario, dark energy accelerates until it tears everything apart. Galaxies, atoms, even spacetime itself. And if spacetime is torn, time, being part of spacetime, would also cease. But here's the thing. Current evidence suggests dark energy isn't that strong. A Big Rip? Unlikely. 2. Heat death. A more accepted fate is the heat death of the universe. All stars will burn out. Black holes will evaporate. Entropy, the measure of disorder, will reach its maximum. No energy, no processes, no change. If time is change, then in this still, dead universe, time effectively stops. So, will time ever stop? So, what's the answer? If time is change, then yes, it will stop when the universe stops changing. If time is absolute, then no, it keeps ticking, even in silence. If time is spacetime, then it dies if spacetime is destroyed, but that seems unlikely. If time is an illusion, then it never existed to begin with. And the question is meaningless. Chapter 8. Entropy and the arrow of time. Maybe the real key is entropy. Time, as we experience it, flows in one direction, forward. Why? Because entropy increases. As long as disorder grows, we move from past to future, from memory to possibility. But once entropy maxes out, time might lose its direction, its meaning, its existence.